Hello, geometers. Welcome to 3.2, which is translations. And yeah, let's get started.
All right, thank you, Ray. Smash that like button and subscribe. Join my Patreon. Special videos posted each week that I can't post on this platform.
Early access.
Yeah. The real answers are on Patreon.
How about buy my Patreon?
All right, so check it out. Just for the record, the real answers are also here. I don't really teach you guys wrong and then tell me, like, okay. All right, 3.2, our focus today is on translations. Now, because it's going to be translations and immediately we're going to define translations, I'm not going to write it here just to avoid being redundant and repetitive. Instead, 3.2, if you want it, it's called translations, but the very first thing that we're going to do is define that with our first topic header. So translations. Cool. Translations. Now, for these, we're going to continue using this wonderful function notation with the a goes to a prime and so forth and so on. But by definition, all that a translation really and truly is it's a mapping, or a function if you would rather, but it simply maps each pre-image point, which remember that is our original. It maps each pre-image point to the image. Okay, by moving, and we're going to sneak in a new word here, along a specified vector. I'm going to sneak that in as a vocab right here. A specified vector. Now, not the same vector that you might find in Despicable Me with the minions and all that, but the same word. Okay, those of you that had my physical science class, you may remember the word vector. I'm not sure. It's hit or miss whether you remember stuff a whole year away, but I'll tell you we did a lot of stuff. We used the word vector, but we didn't do a whole lot of math with it. Do you remember what it is, Lily? Because I see you nodding in agreement.
I remember the word, I don't remember.
Okay, so just a quick example to see if we can recall it from physical science, because I had a lot of you guys in physical science. Velocity and speed are different. If I say the speed is 25 miles per hour, which that's the speed limit, we don't call it velocity limit. Because right now, I'm not going to go 25 miles per hour. I'm going to go to about 1 meter per second, okay? And I'm going to show you two different situations just to see the science idea, and we'll tie it back in. Right now, I'm walking 1 meter per second, right? That's my speed. Everybody cool with that, roughly?
Yeah.
Okay, I'm still walking 1 meter per second. My speed is still the same, but is it the exact same velocity? What's different about when I go that way or when I come this way? From your perspective, is that positive or negative? So do you agree that right now my speed might be +1 because I'm walking in a positive direction? My speed is negative, or my velocity is -1 now. Same speed, but I'm just going the opposite direction, right? So direction matters when we talk about velocity. Direction matters when we talk about force, acceleration, pretty much any quantity in physics. In here, we use that same idea, but we use it with vectors with direction certainly embedded. But let's get a nice definition of this real quick. Now, a vector, and I'm not going to be super duper formal with this, vector, all that it is a line segment with a direction. A line segment with direction. Now, what that means for us, and I'm just going to sketch one out here, and we're going to do it on the coordinate plane, and it's going to be really lazy. We don't need like a perfect thing. Let's say I have point A at the origin, and any point in quadrant 1 where I end, I'm just going to say that it's up here. We'll say this is point B at x comma y. Whatever it is. I don't care what the numbers are. I'm just going to call them x, y. Now, could I draw the segment AB? Yeah, I would literally just connect these two. Now, we're going to build up to it, but I'm going to make that segment first. Okay, so here I have a segment. Now, right now, if I say segment AB, we are all looking at that segment. Could I name it segment BA instead?
Yes.
Yeah, and it's the same, right? Now, vectors, they're not the same. When we look at a vector, If I want it to go from A to B, it is a different, it's in fact the exact opposite of the vector from B to A. Like if I said Lily's forward from me, but from her perspective, weird, okay, hold on, this is gonna be weird. We both say we're forward, but we can't both be right, right? We gotta see where we're coming from in 2. Okay, if I want this vector to have a direction, I'm gonna stack an arrow right here. Now, this right here, this little pink or purple, whatever color you see here, this is my vector. It starts where and ends where? Starts at A, and it ends at B. Now, to write our vectors, that's it. All we need is some direction. Now, the good news is that we don't get crazy with them in here. In this class, our vectors, at least for now, start at 0, 0. Okay, they start at the origin, which is convenient. Which means if I wanted to just start here, and it's always going to be here for our purposes, if I wanted to end at point B, I just need to take some number of steps in the x direction and some number of steps in the y direction. Everybody agree with that? Okay, this is going to feel like a really weird statement. Pretend you're at Disneyland with friends and you're going to take a picture. Somebody's going to take a picture of you. Do you just stand there like this? Show me your most generic Disneyland picture. How would you pose?
Maybe with like.
So there might be a duck face in there, right? Like maybe that's not really that cool anymore, and people don't really do it. That's the kissy face, right? The duck face. Okay. How would you do a peace sign? How do people do cheesy Instagram peace signs? People do this. Anybody ever do this? Something like this. Like people are obnoxious with it. They make them really pointy, right? So I call what we're about to do Instagram brackets or Disney brackets for real, because I think of people doing this. Like something like that. Like it's silly, but it's a pretty generic photo, right? Like we've all seen that picture, I imagine. We're gonna use Instagram brackets or Disney brackets, whatever you want to call them. Pointy brackets is really what they are. When we write this, all we simply need or only need the terminal or the ending point. I'm going to call it terminal here, which just simply means end point. Now, when we write these, there's some notation that we use just by standard stuff. Normally, and we don't get super into it, but it's nice to see it here, the way that we name vectors is with a lowercase letter, and the natural step, or the first choice would be V. V for vector. So I'm going to label it here. I'm going to say this is V, and we'll write this again. But to differentiate, to make sure we can tell that it's a vector and not a ray, which it very looks like it could be, or a segment, we use a specific notation. I'm going to use a half arrow, like this. I'll write it big again. This vector right here, vector V, is written like this. It's a V with a half arrow. This is the notation for a vector. In your textbook, it might be bolded instead of this notation, but I can't really bold here and make it look clear. Okay, when we write vectors, this vector, if it always starts at 0, 0, we don't need to indicate that. It's just implied by this notation. We're going to use our Instagram or Disney brackets. There they are. That's our peace signs that we need. And then all we have to do is say some distance x and some distance y. Essentially, what we see here is wherever we end, just make it an ordered pair, but to indicate that it's a vector, just add those pointy brackets. Okay. Now, we're going to use these very clearly here. Vector stuff, we'll deal with it. I'm going to say that's all I need to say about vectors for now. Okay. They have a direction. It matters. If you wanted to write this thing as AB instead, you could. We would just do AB with that same piece above it. Okay. So vectors, they just say this far, over, and up. That's it. Now, with these, when we denote translations using these vectors, we're going to go back to here. So back to translations, and let's actually get some. So translation notation. Translation notation. Now, I'm going to keep using the function mapping notation where A maps with the arrow to A prime, and we'll specify the rule that we're using. And I really do think I'm going to start using the R subscript. Like R sub X is what they did on the homework, and I like that notation. Okay, for these, we typically use the letter T. So check it out. To translate T on a specific vector, we'll call this one RS. We have it. This is what it looks like. The translation, capital T, translation, and on this vector. And then the only other thing that we have, and we're going to do this in real general right now, I don't love the way your book does this one, but that's okay. Let's say we're going to translate some point A that's already in the form, and we'll just make it, yeah, we'll do x comma y. Okay. Now, the notation is ugly. That's it. Just to make sense of this. You guys remember in Algebra 1 when you did f of x? With f parenthesis x. It's not f times, it's f of, right? This is like the exact same thing. This is the translation. They tell me the rule right here, and we'll clean this up, but I'm doing a translation of which ordered pair? This is like the of part. xy, or that point A that we define as xy. This is no different than f of x. It just looks different because we're talking about multiple things. Now, with this, the rule is super duper easy, and I'm going to show you this right here is the book's notation. I have a very similar notation that I want us to use, but it's that mapping thing. But I want you to be able to deal with both. Okay, this thing, super chill, super easy to do. I know it might not look that way. First thing is that if I translate some point A, its new point has a new name. It ends up at a what? Prime. Now, this next part, this thing right here, how can I tell it's a vector? That RS. The Insta brackets.
Are there any juniors?
Yes.
Camille.
You write that all the time?
Camille and Andrew.
Cool.
Bruh.
Bet. Okay, so this tells me it's a vector. Now, here's the deal. This is like the x coordinate and the y coordinate, right? So this says move in the x direction, how many? What's the number that I have for the x here? R. So all we're going to do is we're going to take the original x that we had, and we're going to add whatever r is. Easy. So if I move 5 to the right, just take x and add 5. For the y value, we're going to do y plus, what does this vector tell me to move in the y direction? S. Ray, you had a question.
Which one is the original? Is the xy the original and the rs is the...
This is our, yep, we're translating along this vector, and we'll do examples here in a second. Now, just to specify, this is how your book presents stuff. So if you're checking answers and things, this is what it's going to look like. I don't hate it. You guys might. And I don't know. Your thoughts on this notation? Anybody else? So do you like it, Raylene, or do you not like it? Okay. I'm okay with it. It's not my favorite. This is the way the book does it. Now, in contrast with that, I'm only changing colors just to show you how it would look in that function notation. Very similar. I like most of the stuff that they have there, but when we do it, we do a x comma y, and when I write it, this is how it'll always, like, I'll give you blanks to fill in on tests and stuff. We're translating along what vector in this one? So here's my notation that I use, because I like this mapping notation. I think it's a little bit easier. A that starts at xy is moved along this vector, and it ends up at a prime, which is still just the x value plus this r, and y value plus that s. These two notations say the exact same thing. This one is much more algebra looking. It looks like a function, which it is a function, but you can see a function in mapping stuff as well. Okay, if that's the book way of doing it, and you don't have to add this, but you might appreciate it. That's the book way. What's this way? This is the hollow way. Huh? Huh? All right, yep. Cool. I'm okay with either. Which one do you want to use in general? I would prefer mine, but I'm flexible. You agree that one's a little nicer looking?
I don't really care. They both kind of bother me just because I really hate writing small stuff in my text. Like the little RS next to the thing.
Oh, well you can do it
and
here.
the above.
Yep, I don't have a good answer for you. All right, let's do some of these. And we'll see that these things are really quite easy. Now, purely honesty here. like real answers. Can you plot points on the plane? Anybody feel like you get goofed up when you're plotting points?
No.
Okay, so on the homework, if you want to use graph paper, you can. But here's the deal. I don't know that we really need to graph them every single time unless you're specifically told to graph it. We can do almost every problem without them, but let's take a look. So all I want to do is translate for each of the following. And I'm going to present it in a couple ways. On A, let's say that I want the following. I want to translate, capital T for translate, along the vector 3, 4. And I want to do that for the triangle RFK. All right. Now, realistically, we can mix and match these two notations. I really do like this notation. I don't know why I'm walking over here to talk to all these people. I really do like this notation that makes it look like a function. It feels more like algebra, which is my preferred stuff. But this notation, it's nice. Now, when we do this, of course, we need to have values. Even if this is what's produced, I think that we should still commit to R, F, and K like this to make sure that we can see that very clear mapping. R, F, K. All right, so here's what we have. We get point R, our pre-image, starts at 3, -2. Point F, Foxtrot, can be found at 0, 4. And point K, Kilo, is at -2, 1. Okay, this is like the whole original setup. Now, for this, I'm going to go ahead and say we have our arrows, and we'll put our rule above it here in just a moment. And then anything in red is just where the actual answer is. In my notation, all I put is the 3, 4 right here. And Ray, it doesn't have to be tiny. If you're using a subscript, it should be, but like right here, I can write them the same size. Just make your arrows longer, but
That's what I did.
yeah.
I just made it
Okay,
bigger.
so check it out. This problem, before we do it, do you think you could do this without me telling you?
Yes.
Okay, so help me out here. Just verify for that. If somebody is struggling in here and they're not comfortable to say they're struggling, then that's an uncomfortable position to be in. You don't want to say anything. I get it. This vector tells me to move how many in which directions? Like in the x direction, what am I going to add to it?
3.
3. Now, if you want to show the scratch work, you can, and I will on one step, this very first one, but normally I think that vectors themselves are easy enough that we don't have to do it. This point becomes 3, that's where we started, plus what?
3.
3, because I have a 3 right here. I've added 3 to the x, which is what this rule tells me to do. X. And how many are we going to add to the y? So, sorry, it was at -2. And I'm going to add 4 to it. This is the math that goes into it. Now, I'm going to erase this here in a second. All I've done is I took my point and I added the x and the y. That's all that we do with translations. Now, I'm going to erase it because I think that we could probably do this mental math. Normally, I won't show that. Help me out here. If I take this 3 and add 3, what do I get?
6.
If I take this -2 and I add 4, I get a 2. Are you guys cool with that? Do the other two for me. Do f prime and k prime, and you might already have them. I'm going to give you like 10 seconds before I do it. Yeah, that's fine. What'd you get, Carson? What is Foxtrot prime?
I did 3, 8.
3, 8. Can somebody second that?
Yes.
Love it. Apple, K prime.
1 and 5.
1 because you added 3, love it. And 5 because you added 4, love it. Doable? Okay.
Huh?
Are we right?
No.
Whoa,
He
I
said 1 and
Wait,
He
you
said
wrote
1. He said 1. I would not have noticed that. It's actually a 1. Good job. Okay. Could you plot these 3 points and draw a triangle?
Yeah.
Could you plot these 3 points and draw a triangle?
Yes.
Do we need to plot these points and draw triangles? No. If you, and I guess we'll know when I ask you to do this on the homework or whatever, if I ask you to draw them, they should be the same shape, same size, but I'm not going to make us do that right now. Okay. We're going to do the bell ringer again. We're just going to look at it, and we don't have to physically write this. If I wanted to, though, and I do want us, and you don't have to add to it, but I just want to make sure that we can see us together. Here's our bell ringer today, and you guys told me it moved how again?
Over 4, up 1.
Over 4, up 1. So if I wanted to very clearly and concisely write what happened here, we did a transformation of this triangle, right? The transformation T of triangle ABC, how did everything move? Over 4 and 1 up. Look at that, we just wrote the rule for it. This is the translation of triangle ABC, 4 units to the right and 1 unit up. We can move really easily here. Everybody okay with that? Okay, should we do one more writing a rule, or if you had to write a rule, could you? Okay, let's verify that. Okay, so for this, you guys are going to help me. We're only going to do 1 point. So on this example, we'll just say write the rule. Okay, and this time, again, only a single point. Raylene, where's your favorite point on the order, on the coordinate plane that's not the origin? 2, 6. And this guy is going to map to A prime, and I don't know the rule yet. I'm going to put a question mark there because that's what I'm asking you to find. This maps to A prime, which is at 37, negative 14. It's moved a lot.
A little bit, yeah.
Cool. All I want you guys to do for me is you're going to find the rule, and the way that you can very clearly write this rule is by simply completing the rest of this. This is T and something here. That's all I'm after. Fill these in. I'm going to give you a moment. If you need a calculator, you're always welcome to grab one. We'll check back in. You better smile really. Oh, you didn't go take your picture. Just kidding. You're good. I felt like I was trying to threaten, but in a fun way.
Can I go to the bathroom?
Yeah, smile.
Want me to say my rule? In case I miss
Sure.
it? I did 35, 20.
35, 20,
Negative.
negative 20. I think that's true, because we just checked the difference between them.
Tis true.
Cool. If we know where we start and where we end, all you have to be able to do to get these is just take the difference, right? How far do we have to move? 37 minus 2 is 35. Negative 14 minus 6 is negative 20. We're done. We can write the rule super easily. Seem okay? All right. I'm going to highlight a property for us, and I want to see how much of this property you guys remember. If it's in this grassy area, you do not need to, you know what? We've done grass before. Have we done grass in here before?
I don't think we have.
Okay, we're going to use the stars instead. If it's in the starry area, you don't got to write it down. This is just scratch work, think work. Okay, if I take A plus B plus C, is that the same thing as C plus A plus B?
Yeah.
2 plus 3 is 5, and 3 plus 2 is 5. What's this property called? Stuff can move. Much like somebody who lives in a big city, they have to get up and drive to work. They commute to work, I think, is the way that we actually say that. They move to get there, they commute. Are these things moving?
Yes.
They are commuting. This is the commutative property is what this is called. Okay, stuff can move. Now, we right now have only been doing single transformations. Do you guys agree with that? Could we do more than one? Like, could I do a reflection and then a translation, or vice versa?
Yeah.
Absolutely. Okay, quick algebra check. And I don't know the answer. I didn't get a clear answer out of 5th hour. Those of you that took algebra 1, I'm going to write something on the board. I just want to know, have you seen this?
Yes.
In algebra 1?
I think so.
Okay, alternatively, you might, and I'm not convinced that everybody has, this might be the other way you've seen it, f of g of x. Okay, so, do you remember a ton about that?
No.
So that's okay. I was not expecting you guys, how confident are you that you've seen it?
100%.
Okay, very cool. I could not get a nice clear answer from the other class, but that's okay. All right, so with that, we are going to be looking at that idea, but through the lens of geometry right now. Anybody know what that's called up there? It's not fog, although it might look like fog.
Circle.
It is a circle. You're not wrong. Okay, that's all right. What we're going to talk about is with that idea, but we're going to do it with algebra or geometry instead. So, our last little piece here, the start of our last piece, we are going to be looking at compositions of rigid motion, or rigid motions, which if you'd rather, remember that lovely word, isometries, could be replaced here. Compositions of rigid motions. All right. Now, when we talk about composing these, all that this really means is multiple transforms. So multiple, it could be 2, it could be 3, doesn't matter. It is multiple transformations or transforms in order. Okay. That's all that it means. Multiple transforms in order. So if you guys agree that I could translate and then get new points and then reflect those points, that's a composition, for example. The notation, just like we saw earlier, which nobody seemed to really hate it. This one's a little uglier. It's more based on our algebra notation here with this F composed with G right here. We have compositions. Those are compositions that you saw in Algebra 1. So, notation-wise, your book is ugly. Your book itself isn't really ugly, but the notation that they use, it's okay. I do think it's kind of ugly, but I probably shouldn't say that because now you're going to think it's ugly just based on my opinion of it. You know what? I think they're awesome and beautiful. Cool. Let's check it out. So here we go. We're going to try and make sense of the following, and we're going to look at a composition. I'm going to have R sub y-axis composed, not an O, this is that little circle, with this thing, T, AB, and then we're going to say it's of this, A, at the point 2, 1. Now, if you wanted to be really formal with it, you should probably put parentheses here, but I don't think your book goes through the process of doing that. Okay, for this, if we break it into little pieces, it's going to be a heck of a lot easier to think about. I'm going to be really loud over here for a minute because I'm trying to make it so that I can hear me still. I have a lapel microphone that I'm going to start carrying around or wearing around. Might need it today. We'll see what the weather does. Tell me one of the transformations that we have.
A reflection over the y-axis.
Okay, we have a reflection over the y-axis. That's that R, right? Okay, Carson, give me another type of transformation. A reflection, and what's that T represent?
Transformation?
So
Or not translation.
translation across, or using which vector?
Like pause the brackets.
And so what's inside of them?
The X and Y.
And so you're right. Do you agree it's AB?
Oh yeah.
And that was a weird question, but I feel like you have all the pieces hit. So I reflect over the Y and I translate. Now, the adding question. Does it matter which one I do first?
Yeah.
It's possible that it does, right? Now, maybe it won't matter here, and we'll have to play around with that idea, but there are some weird stuff that happens with this. With this notation, it's harder to tell, and we can talk about this. It's going to take some work with it, but I need you guys to have this written down, and I need you to have the following. Which of these happens first, do you think?
Probably the X, Y.
Sorry, I'll go here. I won't have my thing. You think the y-axis reflection, like it's 50-50 shot, right?
Just because it's first on the thing.
So I agree with that logic. I don't know that it's right, but I like my head goes the same way. We're transforming which point? Everybody agrees it's A that we're moving. And what's closest to A? Translation or reflection? This is much closer, right? It's right next to it. This is our first operation. Now, it's backward here, and I get that. If you look and recall even a little bit about it, what would happen first? The inside of the parentheses using g of x, or the outside of the parentheses f?
Or inside.
Inside, right? That's PEMDAS. It always starts with parentheses. It's kind of the same thing. We don't write it R of this here, but that's our first step. It is the closest. Now, in this situation, we only have 2 transformations, so there's a maximum of 2 steps. But could I do like 10 of them together if I really wanted? Yeah, and then you just start here. Here's our first step. This is the second furthest away, which means this must be the second step. And I'm not going to write second closest here. You could, but there's like a million ways you could word it. Now, as we look at this, what I don't like about this notation here is it's easy to get lost, especially if we stack up more than these. So if we instead can make sense of this is what happens, I think that it is beneficial if everybody just switches to that other hollow way of doing things. If we did this actual problem here, let's check it. A starts at 2, 1. And using our mapping notation, what do we say was going to happen first?
AB.
So we translate along AB. Now, if I take A and I translate it, my new point is called A prime. And I know that there's no numbers here, but it'd just be 2 plus, what would I add to it? A. And then what would I get for the y value of A prime? 1 plus b. I just take the x's and I add them accordingly. Okay, going further. Notice we only did the first one. What's the other reflection we still have to do? I said reflection on accident already. What's the other transformation we have to do?
Reflection.
It's the reflection. So r sub y-axis. And then big memory time. I'm going to call this a double prime. How do you reflect something across the y-axis? So we're here, and I just reflect to here. Something changed, something didn't.
The X.
The x changed, and what changed about it?
Negative.
It went negative, right? So this one's going to be kind of ugly in general, but it's just a really general problem. If I make both of these negative, there's 2 ways we could do it. We could either do negative 2 plus a, which if you like that, that's fine. Or you could do negative 2 minus a. You could just distribute. I'm fine with this, if you guys are. What's the y value still?
Same thing, 1 plus B.
1 plus b. Now, when I'm actually doing these, this notation I do like, but what I would suggest is if you're like, it's nice to know that this is the function. What I would write underneath of this, if we're doing even more than 1 point, is I would just make sure that I know somewhere here that when I go across the x-axis, xy, just simply changes to negative xy. And you can even include your shortcut here so you don't get lost in the problem. Don't have to, but it's a good idea if you're going to get lost with stuff. Okay. Now, this language, this is the reflection of point A over the y-axis composed with the transformation, or the translation, sorry, along vector AB. It's ugly, kind of blah. Let's do one that's much less general to see if we can make sense of it. So I want you guys to find the following for me. And let's check here. Can you guys think of anywhere that this stuff might actually get used? That's fair. I'm going to be honest, there's times in math where maybe not, realistically. Like, completely honest, math for the sake of math exists. Like, right now, do you want to have a little random talk? I'm not going to give you homework. Okay. No homework tonight.